Right, good morning, everyone. Thank you for all of you to show up here. I'm quite amazed to see how many people are here to learn about trade-offs. This is a bit of a challenge here. The first talk in the first session, you're all pretty sharp still, and I think the session chairs are also sharp still in enforcing the 10-minute limit. So I will do my best to talk to you about our research in the Chaco on trade-offs between carbon, biodiversity, and agriculture. And just to mention from the start that this is a very collaborative project. You see many co-authors here. Some of them are in the room and others at the conference. And Liz deserves a special mentioning here because she has implemented much of the work that I'm showing here on a technical level, and there will be another talk on these more technical aspects on Friday at 10:30 that you can listen to. Now, I'll try to set this up. Well, doesn't matter. So we are interested in deforestation frontiers because these frontiers are typically places where the trade-offs between agriculture and the environment, or agriculture, biodiversity, and ecosystems are particularly strong. And we know a lot about how these trade-offs play out from local scale work. You're all aware of the land sparing and land sharing discussion. There's a lot of work looking at ag intensity and how it impacts biodiversity, but that often focuses on local scale work. And we do understand much less how these trade-offs play out when we look at the regional scale, and this is the scope that we are taking here, trying to understand the nature of these trade-offs at the more regional scale. We focus on the Gran Chaco region. This is a subtropical, tropical dry forest region extending into Argentina, Bolivia, and Paraguay. It is a hotspot of deforestation recently. This is one of the regions where deforestation has progressed the strongest and the fastest, especially since the 2000s, mainly for soybean and cattle ranching expansion. What is particular about the Chaco is also that it is home and it harbors a number of very different land systems. You can see some of them arranged here on an intensity gradient going from more subsistence-oriented smallholder ranching, forest grazing. For those who know the Chaco, this is what's called the Puesto system there, to ranching systems that retain some of the canopy, silvopastoral systems, to more intensified systems, and finally intensified cropping, which in the case of the Chaco often is soybean. So these different systems all are characterized by different actors that do different things. They have different impacts on ecosystem services and on biodiversity, which means they have different trade-offs locally. And now we here ask the questions of how then do these trade-offs play out when we look at the Chaco from a more regional perspective. And in other words, what are configurations of these land systems that would minimize the trade-offs between these three benefits or three ends that we are looking at? And we look at this using a multi-criteria optimization framework. And here you see just some of the specifics on that. This is the study region that we focus on. Here, a big part of the Argentinian Chaco, about 180,000 square kilometers. Our starting point is that we have mapped land systems back to 1985, but here we use 2015 as a starting point. Christian Levers will be giving a talk on the land systems mapping and how we project that into the future tomorrow in the frontier session. And we are interested in three benefits: agricultural production, which we proxy through profits; carbon stocks, we have a carbon map for that region; and biodiversity looks at about 27 birds and 17 mammal species that are of interest and of conservation concern, and we use a biodiversity measure that both tries to make sure all these species are in the landscape and then tries to maximize the abundance of these species in the landscape. We are using efficiency frontiers as a tool to look at these trade-offs, and this is just a very quick run through what these efficiency frontiers are. You see here two of the three dimensions that we look at: biodiversity value, or biodiversity measure, and agricultural profits. This is the efficiency frontier, meaning every point on that frontier is considered efficient or optimal. In other words, for a particular agricultural profit, this is the maximum biodiversity that you can get. For a particular biodiversity value, this is the maximum agricultural profit that you get. So this space is the area of possibility. Combinations of the value of these two dimensions can be reached for the Chaco landscape, or for any landscape. This is not specific to the Chaco yet. And outside, we have combinations that cannot be reached. You can then look at where we are in terms of the actual landscape. It might be here. we can look at alternative futures or policy scenarios. Where would they shift in this efficiency space? And we can also look at how would particular policies, such as, for example, zoning, impact the frontier itself. Yeah? Would it push the frontier into a particular direction? So now this was conceptual, just to highlight what these frontiers do. And this here now shows actual data for the Chaco. What you see here now are, again, 2 dimensions. Now we have carbon stocks on the y-axis and profits, agricultural profits on the x-axis. And the colors here now are the 3rd dimension that comes in the biodiversity score. The more yellow or greenish it is, the better for biodiversity, the higher the biodiversity value is. Now here you can see the efficiency frontier, meaning that when we have high levels of agricultural profits, we have not a lot of carbon stocks, and the colors indicate we also do not have a lot of biodiversity in the landscape, whereas when we are up here, we have relatively low agricultural profits, but high co-benefits between biodiversity and carbon. So this is how to read these graphs. This is our baseline scenario, which is the most flexible one, meaning that all land use transitions are allowed to maximize, given certain targets, the 3 values that we are interested in. The only things that are here locked in are protected areas that we just do not allow to be changed, and we do not consider agricultural abandonment and reverting back to forest, because that's not happening in the Chaco at the moment. Now, what you see here, these little dots show for the situation in 1985, 2000, and 2015 how this particular study region in northern Argentina has been moving in this efficiency space. Yeah? From a situation here towards more agricultural profits, and that has led to a decline in carbon stocks and also lower biodiversity, but only marginally in this case. Keep in mind, this is not showing the actual impacts of the land use changes, but how the possibilities for maximizing these 3 ends have changed. Yeah? So there is a lot of biodiversity loss, but still we have all the biodiversity elements in the Chaco. Relatively speaking, we still can, we are still in a situation where we can keep most of the biodiversity. Now, this is just the same graph, moved it down here, and I'm comparing this now to 3 policy scenarios. And this is the first one, where we explored what happens when you lock in smallholders. One of the big changes in the Chaco is that smallholders have to give way, are bought out. There are also conflicts there as agribusiness moves in. When we lock in the smallholders, we see that the efficiency frontier stays pretty much the same. We're losing a little bit of option space up here in terms of carbon. We're losing a little bit of option space down here in terms of agricultural profits. But by and large, keeping smallholders in the landscape does not diminish the opportunities to strike a good balance between carbon, biodiversity, and agriculture. The second scenario looks at how important are these silvopastoral systems. And we look at this by taking them out. We do not allow anymore to convert to silvopastoral systems. And with this scenario, you can see that the option space changes quite dramatically. We have much less biodiversity in general when you compare the colors here. And we have much less possibilities to reach higher agricultural profits while keeping quite a lot of carbon in the landscape. So these silvopastoral systems are pretty important if you want to strike a good balance between agriculture and the environment in the Chaco. And that considers, our assumption here is that the silvopastures are pretty good for carbon and biodiversity. And we did more work. It looks more into this in terms of sensitivity analysis, and it shows that it depends a lot on what types of silvopastures would be implemented. But for good silvopastures, they can be a big part to the solution of striking a balance. Now the last scenario looks at the current zoning law. For those of you who know the Chaco in Argentina, this is the forest law that basically assigns certain land uses to certain zones. And what this zoning law now does when we consider that in our optimization, then it basically takes away a large chunk of the agricultural profit space, which is what it should do. It should protect areas and should not allow certain agricultural, the most beneficial agricultural systems to expand into this region. So in that sense, the forest law is doing something good. It does also retain a lot of opportunities for finding a good balance between carbon, biodiversity, and agricultural profits to the extent that is foreseen here. Now, with the last thing I want to show here, I would now like to just highlight for the baseline scenario and the silvopasture scenario. Here again, you see the efficiency frontiers, how often these land systems are part of the optimal solution when we look at a particular place for the actual landscapes that we get here. So the colors here mean that we have, if we have high agricultural profits, a lot of land area allocated to the agricultural systems. I'm realizing time is up, and Liz is still comfortably far away from me, but she will come closer, so I'll try to wrap it up here now. What you basically see here is that when we take silvopastures out, they don't play a role. In the baseline scenario, they play a big role, but what you can also see is that regardless of the silvopasture in or out option, forests are always playing a big role. It's always important, if you want to strike a good balance, to protect a lot of forest. And then you can look at actual maps for every one of these individual simulations here and get frequency maps on where forests should be. And that is something that actually policymakers could use for protecting more forests in the Chaco. Okay, I'll leave it at that. Here are some of the things that I said that come out of the work so far for the Chaco, but more generally, I think that these types of tools are really interesting for looking at trade-offs in dynamic frontiers such as the Chaco, learn more about how the actual programming behind it works in Liz's talk. Thank you. Is there time for a question?
Thank you for Tobias. Just before we go to quick questions, if we could possibly shuffle people into the middle so the people on the stairs might be able to get a seat and see the screen at the same time. Okay, and have we got some quick questions for Tobias? Yes, up the back. Yeah.
My question is, with the optimization procedure, it's assumed that every shares the same evaluation system. How does a system like this deal with the winners and losers from the different scenarios?
Okay, so I'll just repeat the question so people on the podcast can hear. So the question was, with the optimization, clearly used to using these things. So the question, if I'm correct, was if with the optimization you're imposing a certain value system, and how do we deal with these different value systems with the different stakeholders?
How do we deal with the winners and losers in the different stakeholders? Because they'll be very different.
Okay, so how do we deal with the winners and losers in the different stakeholder systems?
So it's actually something that Liz is going to talk more about in her talk. So one of the aspects that I didn't talk much about here is that you can use these results and you can actually talk to stakeholders about them, and based on that you can formulate targets and scenarios that can have different value systems behind them. Yeah? For me, going from doing these optimizations based on land cover to having a land systems perspective is going a step in that direction. But I also want to be clear in saying that I'm giving a talk here on optimization. I don't think that optimization should be the only tool for implementing land use planning, for example. Of course, it can inform such discussions, but it can only be a tool in the toolbox for that.
And one more quick question from the front here.
I have a question on the Chaco region which you investigated. You now talk about trade-offs. Did you find any synergies, any, let's say, small-scale agroecological situation in which there is a co-benefit between biodiversity directly and livestock production?
Yeah, so perhaps my language was a bit too negative. When I mean trade-off, I was referring to this from a more neutral perspective, and I think that I showed quite a number of co-benefits, especially between carbon protection and biodiversity protection. But the story at the moment in the Chaco is a story of really strong losses, carbon emissions and biodiversity losses, so that might be a bit of what you can see here too. But some systems, such as the silvopastural systems, they can really strike a better balance than some of the systems that we have expanding there now, and they provide synergies.
Try Microphone on again. Thank you. Okay, so in the interests of getting every speaker to have their full allotment of time, we will press on to Virginia Rodríguez García.
So good morning to everyone. My name is Virginia, and I'm a PhD student at the UCL Louvain. And today I'm going to present a work that I've done together with my supervisor about agricultural intensification and land use change. So with this figure, I would like to explain you our objective. So we try to explain the relationship between cropland intensification and cropland expansion. And we use three theories, land sparing, rebound-effect, and induced intensification. So I will use the green color for land sparing in this presentation. So basically to explain how after cropland intensification, we may obtain a spare of land, and the rebound effect in blue color that will say the opposite. So after cropland intensification, we may obtain cropland expansion. We are also interested on the reverse causal relationship, so from cropland expansion to cropland intensification. That will be explained by the induced intensification theory. Basically, so after pressure on land, we may obtain a cropland intensification. So as I say, our objective was to assess those three theories at a country scale and dynamic framework. And so for that, we set three hypotheses. The first one was that cropland intensity will increase if local pressure on land increases. And we measured that by a negative sign of cropland when yield is the dependent variable in our equations, or a positive sign of rural population density when yield was the dependent variable. Then the second hypothesis was that staple crops will exhibit land sparing, but flex crop or laser crops will be more likely to result in rebound effect. And we test that by a negative sign, again green for land sparing, when TFP or yield, our two measures of intensification, had negative sign when cropland area was the dependent variable, or a rebound effect when the sign was positive. The last hypothesis we test was that intensification that occurs through an increase of total factor productivity is more likely to result in a rebound effect. Now, how we did that? So I used panel data econometrics. My data was, I had around 161 countries and a time period from 1961 to 2016. And we also tried to correct for other issues that we observed in previous statistical approaches. So we use two measures for intensification, yield and also total factor productivity. We use lag variables and first difference estimators to avoid endogeneity, and also we take into account the spurious regression problem that happens when the time series variables are non-stationary. It was our case. So with this approach of cointegration, we found linear combination of them what was stationary, and then so we have the long run equilibrium relationship between our variables, and not only use cointegration to correct for this problem, but we also used an approach from Canning and Pedroni in order to be able to interpret the long run causality directions. So the model looks like this. We had the long run equations and the short run. And basically, with the cointegration and the error correction model, I introduced the residuals into the short run model, which are called the error correction terms, because they allow us to have a better short run estimators. They adjust towards the lower equilibrium, towards the long run equilibrium, sorry. And also, I'm not going to explain it here, but we use this Canning and Pedroni methodology to be able to interpret the beta and the long run, or at least the direction. The results that I got, so I did the analysis at the aggregate level, so all crops together, and 3 group of countries according to their income. And I used the color again, green for land sparing, blue for rebound effect, and purple for induced intensifications. So those are the coefficients that give us evidence of those theories. I will show you at the end a summary of those results. But I also did this analysis at a crop-specific level. So I was taking one crop or a few crops, and I was doing the regression on the main producer countries of those crops. And I did the same analysis. And as you can see, I also got some results on the 3 theories. And this slide, I make a summary. So for land sparing, after doing all those analyses, I got that we found land sparing on the long run and on the short run. On the long run for middle-income countries and some staple cereals. And our hypothesis was pointing towards that. So yes, those crops are low price elasticity of demand. And the same thing for the rebound effect. We also get in the long run and in the short run. So, and for the crops with high price elasticity of demand. And we also got some results from the induced intensification as in the long run for wheat and rice, soybeans, and in the short run for high-income countries and some other crops. To end this presentation, so just to point out that the main contribution of this work was the methodology that we use, that it can also be applied to analyze other complex causal relationship between on land use science, and also the evidence that we got. This is my last slide and a summary of, so in one way, the 3 hypotheses. So you can remind again. A summary of the results, so when it was supported, and some conclusions or remarks. So for the induced intensification, so we saw how in the short run, after increasing population pressure, we generally got expansion of land. However, in the long run, this is the LR, we got an induced intensification, and mostly for low-income countries. And then about the land sparing and the rebound effect. So the land sparing, we got it for middle income and for staple crops. So it was less, we found it less than the rebound effect. And therefore, I guess if we introduce some policies, those results may change. So more land sparing if we introduce some policies, but that's what we got without taking them into account. And for the rebound effect, we got those results for middle, low income countries, and then for a set of countries which were more cash crop, or yeah, and we also saw that it was less strong in the long run than in the short run. So more results on the short run than in the long run. Nevertheless, those results are relative, so not in absolute terms. I can't say anything about the effect on natural vegetation. And as for the intensification through TFP, we saw that it happens in low-income countries, but not for high. And I guess in high-income countries, there are other constraints on land use more important than the total factor productivity, as the use of input. And then we also got some other results as cropland expansion that was induced by cropland expansion induced by an increase of yield for banana, cocoa, sugarcane, oil palm, soybean, and crops with high elasticity. And this may suggest the presence of agglomeration economies on those countries. Thank you.
Thank you, Virginia. Questions? Yes.
Okay, thanks. So the first question was about how I took into account the innovation. I didn't, apart from the total factor productivity evolution in each country.
And how did you attribute that?
I just took the value per year of total factor productivity.
From the past?
Yes.
So you extrapolate the past.
And then the second question was about the conclusions, so which factor more the countries or crops. I'm not sure if I will reply to you correctly. So in my regressions, I choose the crop, and then I choose the countries which were the main producers of that crop. So if the crop was, I don't know, let's say sugarcane, so I choose the main producer's country. I took a rule that I've used always, so 80% of the production or something like that. I don't remember exactly the number.
Okay, thank you very much. So next up, we have a Tomas impersonator because of flight delays. We've got Ralf Seppelt presenting in place of Tomas Vaclavik.
Yeah, Thomas. Yeah, okay. Yeah, listen, thank you very much. I'm not Thomas. Thomas' flight whatsoever, who was expecting Thomas can now move out. Anyhow, I tried to replace him. His flight was cancelled due to strong winds from Prague, so I tried to step in here, which actually will be some kind of complicated thing, and I try to keep with the timeline. His presentation is entitled Farming the Future Planet, which is, of course, a reference to a paper from Jonathan Foley on cultivating a used planet, which was published in 2005. And actually, it's a result of a collaboration we did with people from the Institute on the Earth Economics in Kiel, but also people from the Geography Institute in Munich. And it's resulting, it's more or less the final paper that comes out of this program that we were running a couple of years now on sustainable land management. So what's this all about? So what we already heard this morning is that in the being faced to feed a growing population and also being faced with fulfilling demands in terms of consumption, in terms of food and changing diets, food production needs to increase. And most of the strategies that are suggested so far in terms of reducing food loss, in terms of harvested and raised, or changing diets, they didn't took off that far. So at the end of the day, it seems that increasing production seems to be the predominant story that we are listening to and that we try to address. Increasing production can be obtained by various measures. One, of course, is expansion of cropland, so further land uptake. And the other story that we also heard this morning already in the plenary lectures is the intensification of agricultural production. What we didn't look at so far is how does it play out in terms of biodiversity effects. So what we are interested in this study is actually the trade-off between both of these drivers, expansion and intensification, given the demands in further agricultural commodities to biodiversity and vice versa. And to do so, we did a simulation experiment. So we used a global agricultural trade model, and we assumed two different scenarios. One is solely focusing on expansion to fulfill the needs of a future population, and the other one is solely focusing on intensification. And given those two scenarios, we try to assess what is happening to biodiversity loss and actually what's happening to the global agricultural markets. So our, well, let's say, experimental design that we have starts with these two different scenarios, which is trying to assess the integrated expansion potential. So where could future agricultural production can happen, which is based on biophysical constraints and socio-economic constraints. And the others is based on the possibility of further intensification, which goes mostly back to all the discussions on closing the yield gap, which is nothing else than talking about intensification. And this also bases on the biophysical constraints. And on the other hand, we do have, well, pretty decent data from IUCN that tells us something on the biodiversity on the planet, which actually is species endemism richness, and both things will be compared. We do a hotspot analysis, and we are running a global agricultural trade model that uses a reference scenarios and one which is looking at expansion and on intensification. So let's look a little bit into the details of this design. First of all, we used results from 2007, which tell us something about the crop suitability that can be planted. So we used a model that is able to capture the 17 most important, globally most important crops where human beings are fed with. We consider all suitable area by assessing climate, soil properties, and topography. And we try to assess a cultivated area which is not used so far, and simply mask out urban areas and artificial areas. This is run on a 1 kilometer grid cell with a really effort on sampling design, and associates various crop suitability values on this map, and also uses climate change projections for the next 30 years, which help us to also identify the changes that might happen under an SWS A1B scenario. So we are looking into the future not only in terms of the economy and the dietary changes and the demands, but also in terms of the climate. We fed this into a global agricultural trade model that uses GTAB as a trading base and is all the time calculating equilibria based on the commodity values that we know. So we couple this biophysical model with this DART trade model that accounts for population growth, changes, and consumption patterns, and considers the repercussions between production sectors and regions. So we pretty much know what's happening in each region per commodity and who is trading what to whom. And finally, we use species endemism richness, as I said, which tells you something about a certain grid cell, how important this is for protecting biodiversity. So if there are some rare species on just one single grid cell, then this is highly important for preserving this. If this species is also distributed on a wider area, then this cell gets less important. If it has lots of species there, then it's again higher, has a higher importance, etc. So this is pretty reliable data. It accounts for mammals, birds, and amphibians, and is on a 0.5 degree spatial resolution. We then went back to 110 square kilometers, where this can be downscaled in a reasonable way, but that's actually the highest resolution you have so far being able to do these kinds of analysis. So, and if you apply all this, then it gets really exciting. So that's one of the results, telling us something about a change in global crop production. So what you see here is different world regions going down from the globe, rest of the world, Australia, New Zealand, etc., down to Canada. And in this orange color, you see what happens under our expansion scenario, and this is the intensification scenario. Okay, I'll admit these things happen in parallel. This is really artificial, but let's give it a try and see what the differences are. In terms of the expansion, well, before going further, what you see here is that both bars on the bar are equal. So both scenarios can be compared because they all lead to an increase of 20% more production. So with this fixed point, both scenarios and both experiments are equal, but then we see how they differentiate into various regions. What you see here is that, especially for the expansion scenario, will lead to the fact that in Brazil, in Southern America, lots of area is taken under use, as we've seen in various other presentations before. The intensification scenario, however, increases production in India, in sub-Saharan Africa, in the former Soviet Union, regions where everybody is telling us that there the yield gap can be closed. So that's more or less consistent. What you also see, due to the fact that lots of countries either oh, this one. Okay, well, that's more complicated for me. Okay, the prices, of course, if we increase production, go down. And you can see here how they differentiate. So for India, for instance, prices go down much drastically under intensification scenarios, rather expansion scenarios. And this now, of course, is happening spatially explicit throughout the world. And what we did here is to now look for the that's not on the slides. Thomas would know it. I don't know. So we use an upper quantile of about 10 to 15% of the areas which have the highest species endemism and which are likely to be used under the expansion scenario. And in this square here, you see how many taxonomic groups are affected in terms of endemism richness in the expansion scenario and how are less affected or not significantly affected in the same scenario for the low case. So what you see here is the typical expansion areas which might happen under the expansion scenario, which are also highly species rich, and only 10% of those are currently protected under the IUCN categories. If we go for the intensification scenario, then you see, of course, this area goes down, but the effect of intensification on biodiversity is something that is not fully understood, so we probably need more information there how this intensification really plays out to biodiversity. And at the end, what the most interesting result is, if you overlay all things together, then you could study what are the possible regions globally in the next 30 years which are affected by expansion, intensification, as well as biodiversity, the upper 10% most likely regions that we probably lose
and also those which are overlaid or which are coinciding between expansion and biodiversity, intensification or biodiversity, and so on. So that's something which actually tells you that both scenarios can be identified and could really distinguish various regions which should be treated differently if we think about agricultural markets and further development. Like we said, for instance, India, Sub-Saharan Africa and others compared to South America. So, as actually I'm stepping in for Thomas, I have nothing more to tell here. So our conclusions are to identify these key trade-offs on a global scale. It's a required input to assess SDGs correctly, and increasing production may result in improved food security, but on the other hand, we do see where these regions, where there are core regions which are affected for possible biodiversity loss and can be affected. Yeah, the other part I already said. Well, there's one paper out on it, which is simply looking at expansion, but this one here is still work in progress, where we look at intensification and expansion in parallel. And that's it, and this is what I hope to say, and hopefully Thomas would have made it similarly, at least. Thank you very much.
Thank you. So the last chance for Helmut to make an appearance if he is here. Otherwise, we have a little bit more flexibility for questions. Okay. Okay. So if anybody has any questions for prior speakers as well. Otherwise, we'll, okay. So,
different modes of intensification impact biodiversity so differently, yeah? I guess you saw it coming, but so, I mean, here you have a certain paradigm in terms of intensification implemented, and the impacts also in terms of geography would be really different if you would look at different modes of intensification, yeah? So can you say a bit about that?
Actually, completely true. We didn't say anything about what kind of intensification we really apply, and that's a completely different topic and a topic on its own. What you can relate this to is something like using one of these classical closing the yield gap studies, which is providing you some maps, and here could be done something, which are also not quantifying by which means of intensification these yield gaps are be closed. And we know that these differ throughout the world. And so the only thing is that we do is, assuming there is some kind of yield gap closing happening, how much species would be affected. And this is more or less the framing that is used is something like a conventional intensification type of mode, which is not necessarily the right way to go in various regions. So there's lots of space for whatever.
Okay, and one. Oh, sorry. Yep.
No, not in this one, which is actually hard to do in terms of uncertainty analysis. I could pull out other studies that where we try to tackle the issue, also where we try to tackle what Tobias was just asking, trying to identify the modes of intensification. And there you, of course, see differences. So you see that in more or less forested landscapes, biodiversity is much more robust under intensification methods. You see that various species react differently, that mobile species, of course, react differently to intensification, depending on the landscape structure, configuration, etc. So the pattern is really, really complicated. And in saying so, I would simply point you out to a presentation Michael is giving. Michael Beckman, somewhere around during the conference, which is actually on a meta-analysis that we did to dig into that question.
No, so how we characterize the different land systems that we are looking at the moment is that we use the best data that's available on biodiversity in these systems, on carbon stocks in these systems, and on the, in our case, profits in these systems. And then we use that as our starting point, yeah. We have not explored scenarios of how you could increase profits, etc. Yeah? But yes, in this conceptual slide that I showed, it was this sort of pushing the frontier that could happen, for example, for the profits part. It's expected to happen, yeah. And it could reflect on the other types of trade-offs as well, but we haven't explored that so far. Are you happy with that answer?
Okay, one quick point of housekeeping. The back entrance is now open, so we can use that to enter and exit the room. Otherwise, we will press on to Mark from the Karlsruhe Institute.
Thanks very much, Liz. I think am I working? Yes. Yeah. And do I get?
It signs 5 minutes
Yeah.
and 9 minutes. And
Oh, I thought I had twice as long because the speaker's not here. Oh. I put in some extra slides. Yeah. Anyway, good morning or afternoon, everyone. First of all, I'd like to acknowledge my co-workers, who are the ones, of course, who did most of the work on this particular presentation. And we're going to be talking about large-scale bioenergy production and the potential trade-offs that exist with respect to food security, but also with broader impacts on the environment. And I want to look at a few ecosystem services and the various consequences. So first of all, just to give you some context, most of this you know. You're familiar with the Paris Agreement. So the concerted inability of the world's governments to reduce greenhouse gas emissions probably means that we're going to be committed to some form of land-based mitigation. And one of the options for that is through large-scale bioenergy production, and this has been proposed. So actually, in about 30% of the NDCs, the nationally determined contributions, involve some form of land-based mitigation, so it's going to be fairly important in the future. So what are the consequences of this? So we think it's important in terms of offsetting fossil fuel production or usage, but maybe there are other consequences as well. And we need to reflect, and there's also increasing skepticism about bioenergy. So as we know, we want to implement bioenergy because it's a way of reducing emissions from fossil fuels. Well, this is a quote from Searchinger, but the cost is not using that land to produce other plant outputs, including food and carbon storage. So there are consequences of our actions. And it's possible that the true carbon offset may, in fact, be negative. And of course, large-scale bioenergy could have broader environmental impacts on biodiversity, et cetera, et cetera. So these are some of the major issues as context. So some of the things we need to think about, there are some critical factors. Clearly, there's going to be direct competition between large-scale bioenergy and food and timber production. There's potentially also going to be indirect land use change, so displacing the effects of land use to other parts of the world, the environmental impacts, and we need to be able to assess the true carbon benefit of implementing bioenergy. And this sort of very schematic diagram just tries to demonstrate that there is going to be this squeeze on food production and potentially on forested areas or other natural ecosystems if we increase the area of bioenergy. It's just a simple truth that there is a finite amount of land and we can only use it for certain purposes. So this is what we're trying to evaluate. What will be the consequences of large-scale bioenergy? And this is the methods. There's 3 basic steps to this. We're looking at simulating land use change with increasing bioenergy production. And this is very much based on a stylized scenario that looks at simply, almost like a sensitivity analysis, looking at a range of different areas of bioenergy production as a driver of land use change, with everything else held constant. We're using a model called the Integrated Assessment Platform, which is a spatial explicit model that models land use change amongst many other indicators for the EU 28 plus 2 countries, Norway and Switzerland, soon to be EU 27 plus 3 by the end of the year. I'm reliably informed. And what we're going to do as well with the model is to simulate the impact of these land use changes on broader environmental quality issues, including area of forest land loss, looking at nitrogen, water use, and increases in the use of pesticides through intensification. And we'll look at some of those expansion intensification issues as well. And finally, we're going to try and estimate the benefits of the carbon benefits of replacing fossil fuels with bioenergy. So, straight into some of the results. So this animation, you might see it moving in a moment. If you look at the bottom, you can see this is the area of bioenergy that we're increasing. And this is given as a percentage of the arable area across Europe. And as you can see, as you increase the area of bioenergy, then naturally you're eating into other land uses, and you're primarily using the green areas in this map, which is deforestation. Now, of course, in practice, we recognize that a lot of forests in Europe are protected, so you wouldn't necessarily get deforestation, but we're looking at a stylized experiment to see what would you need to do in order to increase bioenergy up to about 30% in this particular case. So we're looking at fairly large declines in forest area. What does that look like? Slightly complex graph, but if I can show you here, the forest area is this curve along here, the green one. So you can see that that's declining. You see the area of intensive arable increases. That's the area of bioenergy that's increasing over the area in millions of hectares of bioenergy cropping. This is the total land area of the EU 28+2. But also what's interesting here is you can notice that the intensive arable that's non-bioenergy is also declining. Okay? So we're actually squeezing both the food production areas and the forested areas in order to produce bioenergy crops. And that's going to be quite significant when we look a little later on. So in the particular model runs, you also get a very small but not very significant decrease in intensive pasture for dairy areas as well. So what the model is actually doing, it's basically saying it's more profitable to take land from forests rather than from intensive pasture, which has already an economic benefit. And so what we find is for each additional hectare of bioenergy, we're losing almost 0.8 of a hectare of forest. And again, we're also seeing, as I'll show in a moment, as a consequence, also intensification in the remaining food production areas. And that's really critical. So what the model is doing is trying to expand, as we increase the bioenergy areas, expanding the area used for bioenergy, but it's also intensifying food production on the remaining arable areas. And again, so there is a trade-off with food security. What we're noticing as well, if you can try and understand this graph, again, this is the bioenergy area increasing along here in our stylized experiment. This is calorific consumption of food, already relatively high, and the circles show the forest area for different categories in millions of hectares. So again, what you can see is that also we have this trade-off, and this is another important point to consider, that we can also look at changing the calorific consumption, and we can also look at changes in the dietary patterns of consumption of food as well. So actually you would make more land available for bioenergy if society changed its consumption habits, primarily in this case the consumption of meat. So we do know then that there are these trade-offs with food security. And I mentioned that we're also looking at agricultural intensification, because if we intensify, we can produce more food. That provides more land for more bioenergy. That's more or less what the model is implementing here. But of course, the consequences of intensification are manifold. So for example, we found that, again, these are all over the bioenergy area. We found rapid increases in irrigation water in order to intensify crop production, massive increases in pesticide usage, big increases in fertilizer usage, and that leads to nitrogen losses. So a direct and large-scale impact on the broader environment of the intensification processes. So everything at the moment is not looking very good, is it, for bioenergy? So we are losing forest, we're losing the carbon stocks in forests, we're losing biodiversity in forests, we're squeezing the food production areas by intensifying, leading to potential environmental degradation through emissions and use of intensive inputs. So at the moment, nobody'd want to grow bioenergy, would you? No, of course not. But we can look at the benefits. So the benefits are the fossil fuel offsets of bioenergy cropping. This is just a range of data taken from the literature, just to give you an idea of what the literature is saying about the benefits of bioenergy and different types of feedstocks here. So we're looking at everything from soybean, sugarcane in Brazil, maize in the US, et cetera, et cetera. There's lots of different examples here. So there are different feedstocks, different crops that have different fossil fuel offsets. The offset is different also depending on which fossil fuel you're replacing. So coal is worse than gas, therefore you get more benefits if you're offsetting with with coal. So there's lots of different variability in here. But what we've come to, looking at the literature, is that we can envisage something in the region of 0.45 to 6.6 tons of carbon per hectare per year as a reasonable range for an offset of carbon from bioenergy production. And if we look specifically into the European context, then again, for a range of different crop types, we get a similar order of magnitude of the offset for those different crops. So again, we're sort of sticking to this range to give us an idea. We don't know with certainty what the actual offset will be, but we could explore the consequences of the range. So what does that mean in terms of the carbon benefits from bioenergy? Okay, well, as I mentioned, we were looking at declines in the forested area. That, of course, is associated with a loss of carbon, and we calculate this for each additional hectare of bioenergy. We have calculated 272 tons of carbon are lost based on the modeling. And if you look again at the standard graph I'm showing here, the bioenergy area change, you can see the potential carbon stock declines in a fairly linear way with the increase in the bioenergy. Not entirely, sort of levels off at the bottom. So we're losing massive amounts of carbon, right? So let's look at the benefits. Well, if we can calculate also what's called the carbon payback time. So if you get that offset of carbon for every year, how many years would it take before you can offset the carbon that you're losing because of land use change? And as you could probably see, so that the two curves here show the ranges of values of assumptions about the carbon offset benefits that I was showing you earlier. But what you can see, again, across these areas of bioenergy, that most of the payback times, this is years since today rather. So what you can see is we've got decades to centuries of time required to offset that magnitude of carbon loss due to the land use expansion. So it doesn't look really good at all, does it, all round? So from an environmental perspective and from a carbon benefit perspective, bioenergy in Europe is not looking good. One of the important points I forgot to mention earlier is when we did this analysis, we prevented the model from importing additional food. Of course, we did that because we don't want to displace the effects of bioenergy production in Europe to other parts of the world. So just having deforestation elsewhere. So even though this is an artificial experiment, it does to some extent portray the types of processes that are going on. It may not be European deforestation that's happening, but it could be deforestation in some other part of the world. So just to sum up, time's up. My last slide. Again, just to reiterate, we're looking at a large loss of deforestation for every increase in bioenergy associated with a large carbon stock lost. It could take decades to centuries to restore that loss of carbon. This clearly will have strong impacts on biodiversity and potential impacts on food security, as well as the broader environment through the intensification of food production on the remaining land. There's a couple of ideas for further work, but I'll leave it there. Thank you very much for your attention.
Questions?